method to analyze the indeterminate structure. This method is invented by Professor Hardy Cross in 1930, and this method is very simple and it is widely used in engineering for the calculation or to analyze the indeterminate structures. Okay, so the description of the method. Now imagine that a frame is there. Now suppose this is a center point of the frame. Now I will draw the members. This is one member. Let it be, this is point B. Then here, this is the another member of the frame. Let this point is A. And then here, this is point E. And now here it is point D. And here it is point E. This is D. And this point is C, and let it be this center point is F. Now here in this given diagram we have 5 members. Okay, the members are AF, then BF, then CF, BF and EF meeting at point F. So all joints A, B, C and E are fixed. So here A, B, C, D and E, all these joints are fixed joints, and while joint F is a hinged joint which permits the slight rotation of the member. Okay, slight rotation of the member is permitted here. We can say that hinge is provided at point F so that the rotation is permitted, but the deflection is not allowed. Now if you see the algebraic sum of the moments of all all the members coming onto this point F, that moment is denoted like this M. But in actual, if we see that in actual, this moment is not equal to 0. We always use the equilibrium equations that moment at any point is equal to 0. But in actual, if you see that if these types of members are there, it is connecting at point F, the moment which is introduced here at this point actually, in actual, this moment is not equal to 0. So this moment, if the joint F is not fixed one, the fixity assumed is to be for due to the imaginary clamp. So we can say that this is hinge support. We have already told you imaginary clamp. We also can consider this. If we release this clamp here, if we release the clamp here, imaginary clamp, let this is be our imaginary clamp. Okay, if we release the moment at this clamp, then what we will get, this results in the modification of the moment at point F, and the modification of the moment also far end at the different points A, B, C, D and E. So in short, we can say that this M is nothing but it is unbalanced moment. Unbalanced moment. This M is nothing but unbalanced moment, and the algebraic sum of the fixed end moments and the modification factor give the final moment at the joints. So we have to add some modification factors, and after adding those modification factors we will get the final moments at these joints, and we can solve that indeterminate structure. Okay, so after this the next point come into the picture, that carryover moment. So next point is carry over moment. So now what is the meaning of this carry over moment? Okay, so we will derive some expression for this. What is carry over moment? Now so consider this beam now. Okay, here the hinge support is provided. Let it be this is our point A. Here the fixed support is provided. This is point B. And now if we apply here a moment, okay, let it be this moment is MA, which is applied at point A. So now due to this moment, the beam will be deflected like this. This is the deflected profile, or we call this as a elastic curve, as we have seen in the previous chapters. So now suppose at point A, if I draw the tangent, So let it be, this is the tangent at point A. Now the angle between the horizontal and tangent, we know that this angle is theta. Okay, so now here if I draw the M over EI diagram of the above beam, then the M over EI diagram can be drawn. Here how the M over EI diagram we can draw. So this is here. Here is the moment MA. Okay. Now suppose here if here also the hinge support is provided, then I can directly here this point I can directly join to this point. Okay, so this is our point A and point B. What I want to say, if here like this also hinge support is provided, then we can join these 2 points here in a straight line. But if you see at support B, here is the fixed support is provided. Okay, and also due to the moment applied at point A, we assume that some reactive movement is generated here at point B. Okay, and let this moment is MB, but this MB is generated due to this MA. Now actually what we want to do, we want to calculate what is the value of this MB. Okay, so for that now here, so see see the sign convention. Now this moment is in this direction, so it will try to sag the beam, and we have assumed MB also in the same direction. MB is also try to sag the beam. Okay, so this ordinate is our MA, and here I will take our second ordinate, and this ordinate is MB. Now I will join these 2 points. Okay, so now I can call this, if I divide each ordinate by EI, so MA divided by EI, and here also MB divided by EI, then I can call this diagram as M over EI diagram or M by EI diagram. Now so this is the trapezoidal. I will draw this line so that this area is get divided into 2 triangles. This is our first figure, first triangle, and this is second triangle. This is the second triangle. Now if you see this original beam, here the hinge support is provided. So at hinge support, deflection is always 0. Okay, so the value of delta A at this point is 0. So here we know that from this beam our delta A, theta A is present over here, but delta A is 0 because hinge support is provided. So delta A is equal to 0. This is our equation. Now if I use moment area method to calculate the deflection by using this M over EI diagram, I can generate one equation. So here delta A is equal to, now this is our first area. So first area, it will be half into height is half into base into height is our formula. So MA by EI into L. Okay, MA by EI into L. Now this is the area. Now this triangular area is get converted into the point load, and it will act through the CG of this figure. But as we are taking calculating the delta A, we have to take the moment of this area. So moment of this area from this point here A, the centroid will be at a distance of L by 3. So multiply this by L by 3. Okay, in the similar manner now consider the second area plus second area is again this is the triangle. So again I can write over here half into base into height. So MB upon EI is my height into base is L into, now here is the 90-degree right angle triangle. So from point A it will be at a distance of 2/3 of L. So 2L by 3. Okay. So if you further simplify this, then we will get delta A is equal to, so delta A is equal to, it is MA L square divided by MA L square divided by 6EI plus, if you simplify this now, this 2 will get cancelled, and here it is mb L square upon 3 EI. So now further solving this, now we will solve this further. Now here you can see, so therefore now if we put here, if we send this term, MA term to this side, because we know that delta A, the ultimate value of delta A is 0. We know this. So we will send this ML square upon 6A to the left hand side. So what do we get now? Here it is MBL square upon 3AI. So we will get MBL square upon 3EI, which must be equal to minus MAL square upon 6EI. Okay. So after reshuffling the term, this L square will get cancelled. This EI will get cancelled. If I send this 3 there, then I will get MB is equal to minus 1 by 2 into MA. Okay, so finally I can write over here MB upon MA is equal to minus 1 by 2. So here negative sign means we need to change the direction of MB. So here initially what we have assumed that MB is in this direction, it will sagging the beam, but now in actual, after solving this, we can say that the direction of MB is like this. Okay, so initially this is our assumed direction. Okay, and now this is our corrected direction as we got the minus sign. This is the only meaning of the sign. Now if you see that if you apply MA moment here, then the moment generated MB here, it is in the same sense. Now see, this moment is clockwise, this is generated also clockwise. Right now we have solved it. And what is the factor? It is this MB moment is MA by 2. If you see here, it is MA by 2. So here this 1 by 2 is nothing but this 1 by 2. This is nothing but this is called as carryover factor. And this MB, this is known as carryover moment.